Okay, continuing on our discussions dealing with support vector machines, let us see how SVMs can be used towards pattern recognition problems. Towards this discussion we will need the concept of inner product kernels that involves Mercers theorem, etc. So, let us delve into these discussions in today's lecture. Okay. The idea behind SVMs hinges on two important things. The idea behind SVMs hinges on two important things. First, there is a nonlinear mapping of an input vector into a higher dimensional feature space which is hidden from both the input and the output, and we need the construction of an optimal hyperplane in lieu of one. So, there are two important details here. One, we need to lift an input vector from the original input space to a higher dimensional feature space non-linearly, and then once we are in the feature space we need to bring in this notion of optimum hyperplane towards the separability problem, right, pattern separability problem. So, this is how we can sort of visualize this mapping. We have a bunch of points in an M0 dimensional input space, and these points are non-linearly mapped to another set of points in an M1 dimensional space, and M1 we can assume it is greater than M0. I can also put the equality here, but typically we will live with this inequality strictly that M1 is greater than M0, but in general you can think of nonlinear transformations where M1 equals M0. Okay. Now, this phi acting on this vector xi can be represented as coordinates in an M1 dimensional space given by phi 1 of xi so on till phi M1 of xi. So, these are all the coordinates. They are the coordinates in the feature space. The notion of nonlinear mapping is a consequence of Cover's theorem. We studied Cover's theorem in an earlier module, and Cover's theorem guarantees linear separability of patterns with high probability when the input patterns are non-linearly transformed into a higher dimensional feature space, right. When we go to a higher dimensional feature space using a non-linear transformation, with high probability we can guarantee linear separability of these patterns. And this idea from Cover's theorem coupled with the idea of SVM design using optimum hyperplanes that are essentially with playing with linear constraints, we can solve this pattern separation problem, pattern separability problem by taking inputs, lifting them non-linearly into a feature space and then applying the SVM there in the feature space towards the task that we want, right. This is the general idea. Now, how do we accomplish this? Towards this idea we need the notion of what we call an inner product kernel. Let X denote a vector drawn from an input space which is of dimension M0, let phi j of x j equals 1 to m1 denote a set of non-linear transformations from the input to the feature space. This is very important. I have a feature vector in an m1 dimensional space, therefore I have coordinates j equals 1 to m1 and each coordinate basically represents a nonlinear mapping, and it is the same mapping but acting on this vector. So the j can be different, right, j can be from 1 to m1, so different coordinates, so I can have different sort of mappings at each coordinate, right, the functions can be different at each coordinate. Now phi j of x is defined a priori. I think this clarity will become I think this concept would be more clear once we discuss an example of these inner product kernels and what these feature spaces are, particularly when I discuss the solution to the XOR problem using SVMs. There I think you will get the clarity behind what I am talking. But in more abstract terms, so you can imagine that I have a transformation and I have phi of x is basically a vector in m1 dimensional space with coordinates phi 1 of x so on till phi m1 of x, and each coordinate can be a function of this vector x, right, and it is a scalar quantity. All these phi j's are basically scalar quantities and phi of x is basically a vector in the feature space, and that is an important detail. Now I defined what this feature vector is, but I have not linked this feature vector to the kernel. So we will evolve this idea. Given a set of nonlinear transformations, we would like to construct a hyperplane that can act as a decision surface, right. I have not gotten into the idea of the kernel yet. I will discuss that when I get into Mercers theorem, but imagine from the kernel you get this feature vector, and this feature vector is in this feature space and it is an m1 dimensional vector and it has coordinates 1 through m1, right, and given a set of nonlinear transformations, since I am interested in an optimum hyperplane for linear separability based upon the feature vectors that are nonlinearly that are obtained through nonlinear transformation from the input vector x, I want to construct a hyperplane in the feature space. The equation for the hyperplane is given by summation j equals 1 to m1 wj phi j of x plus bias, right, this is the bias, and I have this weight vector wj comprising of components w1 so on till wm1. Now this is the equation of the hyperplane which has weights connecting the feature space to the output along with the bias b, like what we have done earlier when we discussed MLPs, etc. Now we can simplify this equation in a more compact form by folding the bias also within the weights. So what we do is by folding the bias we will end up with this equation summation j equals 0 to m1 wj times phi j acting on x to be 0, which is in this form w transpose times phi is 0. You can also take the transpose of it and say phi transpose w is 0 in whichever form that is convenient. Now what we have done, we have folded the bias into this linear equation by setting w naught equals the bias and phi naught of x to be 1. Now with the augmentation, that is by folding the bias, phi of x is basically phi naught x, phi 1 x dot dot till phi m1 x. This is a vector in R m1 plus 1 dimension, because I am folding the coordinate that corresponds to the bias, and phi naught of x is 1 to have the validity of this equation. So in effect, what is happening here? The vector phi of x is basically the image of x induced in the feature space, and as a consequence of that we need to figure out a hyperplane W such that W transpose phi is 0, that is inner product of the weight vector W and the feature vector phi of x, that has to be 0. That is the equation of the hyperplane. We saw during the derivation of the SVM for linearity, for linearly separable patterns, there was condition 1 there in that expression, where I formulate the Lagrangian and I take the gradient, I take the derivative, partial derivative of the Lagrangian with respect to the weight vector, and I set that equal to 0 for optimality. So that gave me this equation. So upon doing matrix differentiation, matrix calculus, I get W to be equal to summation I equals 1 to n alpha I di times xi, that is what I got. But now this xi is not the input vector, but it is a vector that is acting in the feature space. So xi would be replaced by phi of xi when we discuss when we deal with the problem where we invoke the nonlinear mapping, right. So that is what we have straightforwardly from condition 1 in the derivation of the Lagrangian. By using this nonlinear transformation on xi, we land up with the weight vector W to be summation I equals 1 to n alpha I d sub I times phi of xi. So just notice this. Notice this detail, okay. I call this equation 2. Now plugging equation 1 in equation 2, right, W transposed phi of x is 0. So therefore the transposition happens on this phi of x. So W transpose is basically summation I equals 1 to n alpha I di phi transpose of xi, that is what I have written here. So that quantity times phi of x is equal to 0. Now I have an inner product of two vectors, which is phi of x with phi of xi. So this is my inner product. And this is an inner product of two vectors induced in the feature space by the input x and pattern xi in the training set. Okay, this is an important detail. So this is how we would build this relationship. Now we are sort of there to define this kernel, but I have to link this kernel with more intricate properties as to how this kernel can be, what are the properties of this kernel, etc., for which I require Mercers theorem. But before I get into the details of Mercers theorem, so let me bring this clarity to you that I can take the inner product of x, phi of x with phi of xi, and I define that to be my kernel K with two arguments x and xi. Xi is a vector in the feature space, sorry x xi is a vector in the input space, and x is also another vector, and they are linked via this nonlinear transformation. Okay. So, writing it compactly, this kernel is basically summation j equals 0 to m1 phi j of x times phi j of xi, where the index j indicates the coordinates. Now, this kernel is symmetric in the arguments, and you can straightforwardly verify this result. So, k of x comma xi is k of xi comma x for all I. And if you also recall the properties of kernels when we discussed regression estimation, right, we said that we need two important properties. One is the normalization constraint and other is the symmetric constraint, and interestingly this property is endowed in this notion of this kernel here as well. So, in terms of the kernel, the optimum hyperplane is now given by summation I equals 1 to n alpha I di times this kernel k of x comma xi is equal to 0, and I call this equation. This is straightforward, and how am I getting this? This is from this equation here, right. So, I call this possibly equation 2b, right, and just rewriting 2b in terms of the definition of the kernel, I get this equation 3. Okay. So, I did not bring in this notation 2a here, I subsumed the a into equation 2. So, alright. So, this is the equation of my optimum hyperplane. So, given the kernel, the desired response d sub I and the Lagrange multiplier alpha I can compute the optimum hyperplane in this manner. So, with these tools we are now taking slightly a different route into Mercers theorem, and this was a theorem that was established by Mercer in 1908, long back in the last century. I will discuss the statement of the theorem, some conditions there, and how that result is sort of valid to what we are trying to establish here. Okay. Let k x comma x prime be a continuous symmetric kernel defined over the interval a comma b. It is a closed interval. So, both variables x and x prime are defined over the closed interval a comma b. This kernel k can be expanded as follows. It is a summation I equals 0 to infinity lambda I times phi I of x, phi I of x prime, and lambda I is greater than 0 for all I. This is basically like an infinite summation, and someone seeing through this can sense that these phi i's are sort of like the eigenfunctions and lambda i's are the eigenvalues. Okay. Now, for this expansion to be valid, when we discuss series expansions, we have dealt with many such expansions like Fourier series, wavelet series, etc. Right. So, when we think about any series expansion, if the expansion has to be valid, there should be certain conditions that have to be satisfied. From analysis perspective, for this summation to be valid, that is, for it to be absolutely and uniformly convergent, this double integral over from a to b over the kernel times psi x times psi x prime, this has to be greater than or equal to 0, and this integral from a to b psi square of x dx has to be finite, right. These are the two conditions that have to be satisfied for the expansion to be absolutely and uniformly convergent. Now, taking sort of a vector field to this problem, this psi of x, which is a scalar function, can be thought of as an inner product of two functions phi x. I mean, it is basically the induced the function psi of x, which is scalar, can be thought of as the induced self norm of a vector phi of x, where phi of x is given by phi naught x so on till phi infinity of x. It can be an infinite dimensional vector. So, let us take a finite case and see how this can be realized. Suppose we define psi of x as a function 1 plus x whole square over the interval 0 comma 1, this is a closed interval. I can expand 1 plus x whole square as 1 plus 2x plus x square, and this can be thought of as a dot product of two vectors, one on the first coordinate, root of 2x in the second coordinate, and x on the third coordinate. So, you take the dot product of these two vectors, you get 1 plus 2x plus x square. So, this scalar valued function can be expressed as an inner product of two vectors. Now, these functions phi I of x are called the eigenfunctions of the expansion with the corresponding eigenvalues as lambda i's. Okay, so, lambda I phi I are like the eigenpair. Lambda I is greater than 0, which is we assume if lambda I is greater than 0 and it is strictly positive, then this kernel k x comma x prime is positive definite. And one can generalize this notion of kernel that I discussed here for a single variable case to possibly a multi variable case, right. X need not be a scalar and x could be a vector. Okay. So, I took the expansion 1 plus x whole square. So, instead of this I could do 1 plus x transpose x power 2, where x is a vector, say belonging to some dimension d. Okay. So, this is a straightforward extension that one could do for kernels that act over vectors. Now, what is the link with Mercers theorem and what we are trying to do here with these inner product kernels? So, in light of Mercers theorem, for lambda I not equal to 1, the ith image root lambda I phi I of x induced in the feature space by the ith coordinate in phi of x. Recall phi of x is a vector, phi acting on this vector x is a vector, and that has coordinates phi 1, phi 2, phi 3 so on in the feature space. So, now this image, the ith image, which is root lambda I times phi I of x induced in the feature space by the ith coordinate in phi of x, is an eigenfunction of the expansion. This is an important detail. And in theory, the dimension of the feature space can be possibly be infinite. This is useful from analysis perspective in mathematics, but when we deal with machine learning problems where data sets have finite dimensions, then we have to look at expansions over terms that are finite. So, there is something very important and useful from Mercers theorem. Mercers theorem tells us if a candidate kernel is actually an inner product kernel in some space, because it has to satisfy certain properties for absolutely and uniformly convergent, right. And if it satisfies the Mercers theorem conditions, then it is admissible within the SVM design framework, and that is a very important link, right. We were in the input space, from the input space we went to the feature space, and in the feature space we were thinking about classifiers etc., and the optimum hyperplane could be realized in the form of an inner product kernel, and this inner product kernel had to be defined as an inner product of two vectors obtained through nonlinear transformation from the input space, and that is an important detail. And the kernel has to be satisfying certain properties, and the properties that the kernel has to satisfy should obey the conditions in Mercers theorem, and that is a very important link. Okay. Having seen the links between the input vector, the feature vector, the inner product kernel, and the conditions this kernel has to satisfy according to Mercers theorem, let us look into some examples of how one can construct inner product kernels, right. I will take a couple of examples here. So, we can have a polynomial learning machine for which we can think of the inner product kernel to be of the form 1 plus x transpose xi whole power p, and you can expand this using your binomial expansion, and the power p can be specified a priori, right. If p is large, the number of terms in this binomial expansion tend to be large, therefore, naturally I will be getting into a higher dimensional space, right, and therefore I can guarantee hopefully a classifier, a linear classifier that can separate the patterns. One does not have to be restricted to the polynomial learning machine, one can have radial basis functions. So, here we have this in the form exponential minus 1 upon 2 sigma square, the Euclidean norm of x minus xi square. Here sigma square is the spread parameter. As we discussed during the RBF network design, sigma square can be common to all kernels, and this could be specified a priori, or we can estimate it adaptively. This is a more preferred method, that we estimate sigma square adaptively and then fold this within the RBF. So, this is also a possible inner product kernel. Okay. We can also think about the tan hyperbolic under certain conditions over the parameters of the tan hyperbolic, that can also be an inner product kernel. and we will revisit some of these cases as part of the homework exercise. Okay. So, we will stop here.